Imagine for a second, right, that you are a lead animator on a massive multi-million-dollar video game.
Oh, yeah. High stakes.
Exactly. You've spent weeks meticulously designing the 3D model of your main character.
Right.
The armor looks phenomenal. The textures are totally photorealistic.
Everything looks perfect.
Right. So you boot up the physics engine, you make the character twist their arm to swing a sword, and suddenly the geometry of their shoulder just completely collapses in on itself.
Oh, man. The worst.
It pinches down to this jagged, paper-thin point, just completely ruining the illusion of a solid body.
Yeah, in the industry, they actually call that the candy wrapper effect.
The candy wrapper effect,
Wow.
because it looks exactly like a piece of foil,
Yeah.
twisted in the middle.
Exactly.
Now imagine jumping from that video game studio over to a massive chemical refinery.
Okay, quite the jump.
Right, but stick with me.
Yeah.
The engineers there are trying to calculate the exact temperature and pressure where a really complex fluid mixture will boil.
Which is incredibly complex math.
Right. But their computer models keep throwing out garbage numbers. And it's because the simulation involves subtracting two incredibly tiny fractions, and the computer's processor literally just loses track of the decimal points.
Yeah, two completely different domains. I mean, one is digital art and character rigging, and the other is industrial fluid thermodynamics.
But they're crashing for the exact same underlying reason, aren't they?
They absolutely are. It's because the mathematical tools we traditionally use to tell computers how things change and, curve in space, they are fundamentally flawed when you push them to their absolute limits.
And that is exactly where we are going today on this deep dive. But before we jump into the solution, I want to take a second to speak directly to a very specific group listening out there.
Oh, yeah?
I'm talking to the Bussin Sigma scholars of Edward Little High.
You guys know who you are.
We know the kind of academic rigor you bring to the table. I mean, you aren't here to passively absorb trivia. You have a drive to master the complex, top-tier knowledge that fundamentally sets you apart from the crowd.
The real cutting-edge stuff.
Exactly. You're looking for the underlying code of reality, like the elite toolkit that turns the impossible into the solvable.
And this deep dive is completely custom built for you.
It really is. We're going to look at the mathematical cheat code that fixes that collapsing video game shoulder, solves the chemical plant's boiling point, and get this, even allows a robot to parallel park a car with 3 trailers attached to it.
Which sounds impossible, but it's not.
Right. So to give you that toolkit, we're anchoring this entire conversation on a single, highly dense foundational statement from the literature.
It is a heavy sentence, I won't lie.
It's dense, but it's going to serve as our map.
Yeah.
So here is the statement we are decoding today. Let me just read it out.
Go for it.
Quote, "The algebraic geometry perspective that nilpotents implement Taylor expansion algebraically, retaining a finite jet rather than only exact solutions, has practical industrial applications." End quote.
Yeah. That is a wall of academic jargon.
It really is.
Yeah.
And if you are hearing that and thinking it sounds completely impenetrable, just stick with us.
Because by the end of this hour, you're going to understand every single mechanism inside that sentence.
Every word. Let's tear it apart. We need to start with the front half, right? The algebraic geometry perspective and nilpotents.
Yeah, we really should define our terms here first. When we talk about algebraic geometry, we are talking about a major synthesis in mathematics.
Okay, break that down for me.
So historically, geometry was physical, right? You took a compass and a straight edge, you drew shapes, and you physically measured the angles.
Very tangible.
Right. And algebra was about equations, variables, rings, and ideals. It was abstract.
Just numbers on a page.
Exactly. But algebraic geometry smashes those two worlds together. Instead of drawing a physical curve to try and understand it, you define the geometric space entirely by the algebraic rules.
So like the ring of polynomial functions that govern.
Yes. You are translating physical space into pure algebraic structure.
Which brings us to the absolute magic word in our foundational quote, which is nilpotents.
This is where it gets fun.
Right. For the scholars tracking with us, a nilpotent is an element in a mathematical system. Basically, a number that is not 0. It holds a real value.
Right.
But, and this is the crazy part, if you multiply it by itself, if you raise it to a certain power, it completely vanishes. It equals 0.
It's wild. It forces you to basically unlearn standard arithmetic for a minute.
Because that breaks the rules. Right?
Yeah. I mean, if you take a standard real number, let's say 5, and you square it, you get 25. The only way a real number squared equals 0 is if the number itself was 0 all along.
There are just no exceptions in the real number system?
None. But mathematics is not limited to just the real number line. We can construct brand new algebraic systems simply by defining new rules.
Okay.
And we can build something called a dual number.
Walk me through the actual mechanics of that. How do we build a dual number?
Okay, so we take the standard real numbers that we all know, right? And we adjoin a brand new element. We usually denote this new element with the Greek letter epsilon.
Epsilon.
And we declare a foundational, unbreakable rule for this new system. We declare that epsilon squared is exactly 0.
Okay, I need to stop you there. Because my immediate instinct is to just reject that premise entirely.
A lot of people do.
I mean, you're telling me mathematicians just invent a symbol, declare it equals 0 when multiplied by itself, and the wider scientific community is just okay with that.
I know how it sounds.
It sounds like mathematical cheating. It feels like you're bending the rules of reality just to make complex equations disappear when they become, inconvenient.
And that skepticism is entirely natural. Actually, historically, people reacted the exact same way when complex numbers were first introduced.
Oh, really?
Yeah. When mathematicians invented the imaginary unit I, where I squared equals -1, people call it absurd. I mean, they literally said you can't have a square root of a negative number in the real world.
Right, because a negative times a negative is a positive.
Exactly. But it turned out that those imaginary numbers perfectly model alternating current in electrical engineering. They model wave functions in quantum mechanics.
So the fake math ended up describing real physics perfectly.
Exactly. And nilpotents are the exact same thing. It is not cheating. It is a rigorously defined algebraic structure. We use it because this nilpotent structure flawlessly models infinitesimal changes.
Infinitesimal, like microscopic shifts in the system.
Yes, tiny changes in a way that traditional real numbers physically cannot model.
Because on a standard number line, if 2 points are infinitely close together, they just collapse into the exact same point.
Right.
The distance is literally 0. You can't represent a gap that is infinitely small but still somehow exists.
Precisely. The real numbers are a continuous continuum, but in the world of Weil algebras, which is the overarching mathematical category that dual numbers belong to, this epsilon element acts what we call an infinitesimally thickened point.
An infinitesimally thickened point.
Yeah. It gives a single point on a graph a tiny localized halo of fuzziness. It has a direction, it has a slope, but it has no measurable distance.
Okay, let's look at the actual mechanics of how this dual number behaves when you do math with it, just to make it concrete.
Sure.
So a dual number takes the form x equals x sub 0 plus x sub 1 times epsilon.
Yep.
The x sub 0 part is just a standard real number, like a 5.
Right.
And the x sub 1 part is also a real number, but it's acting as a coefficient attached to our epsilon.
Exactly. Now, watch what happens when you actually multiply two of these dual numbers together.
Okay.
Let's multiply our x by a second dual number. Let's call it y equals y sub 0 plus y sub 1 epsilon.
Okay, so we're just doing standard high school algebra here. We all it out.
Exactly. First, outer, inner, last. If you all that out, you get 4 terms. You get x0, y0 plus x0, y1 epsilon plus x1, y0 epsilon plus x1, y1 epsilon squared.
Okay, but because of the golden rule we established earlier that epsilon squared equals exactly 0, that last term at the very end instantly becomes 0.
Boom. It's gone.
Which means it completely obliterates the x1, y1 term that was attached to it.
Completely vanishes.
The entire back half of the equation just disappears. So we're left with the base numbers, x0, y0, plus a combined middle section that has the epsilons.
Right, which is x0, y1 plus x1, y0, all times epsilon.
And anyone who has survived a first-year calculus class is going to recognize what just emerged from that algebra.
Oh, absolutely.
That term attached to epsilon, the x0, y1 plus x1, y0 piece. That is the exact formula for the product rule for derivatives.
Yes. The dual number system automatically calculated the exact derivative of the multiplication just by following the basic arithmetic rules of epsilon.
That is wild. I want to make sure the mechanics of this are crystal clear for the scholars. Think of a nilpotent as a self-destructing math term.
I love that analogy.
Right. It lives exactly long enough to capture the rate of change, the slope, the momentum of the curve. And then the very moment it hits the second power, the moment it tries to become a larger area or volume, it self-destructs.
It vanishes.
It vanishes perfectly. It leaves absolutely no messy, infinite decimal trails behind.
Self-destructing perfectly captures the utility here. And this points us to a really profound theoretical shift mentioned in the literature regarding the Fermat property, or Hadamard's lemma.
Okay, unpack Hadamard's lemma for us.
So let's look at how classical calculus finds a derivative. It relies heavily on the concept of a limit.
Right.
You take a point on a curve, you pick a second point slightly further down that curve, you calculate the slope between them, and then you basically drag that second point infinitely closer to the first one.
And you watch what value the slope approaches as the distance shrinks towards zero.
Exactly.
Yeah,
But algorithms absolutely hate limits.
because a computer can't actually do infinity.
Right. A processor is finite. It can only do incredibly tiny fractions. So a computer takes a step size, maybe 0.000001, and calculates the difference.
Which introduces massive problems that we will get into shortly.
Oh, massive problems. But Hadamard's lemma proves that you can characterize smooth functions purely algebraically.
What about the limit?
Exactly. It states that the difference between a function evaluated at 2 points can be factored algebraically into the distance between them, multiplied by a unique difference quotient.
Okay.
So by utilizing the structure of these C-infinity rings, which include our dual numbers, we can derive the entire foundation of differential calculus without ever once using a limit.
No infinitesimally shrinking gaps.
None. Just pure, rigorous algebra.
So we have this self-destructing number that bypasses all the messiness of limits. How does this translate to actual on-the-ground engineering? I mean, if I'm programming a computer to model the aerodynamics of an airplane wing, why do I care about dual numbers?
You care deeply because calculating complex derivatives on a computer usually forces an engineer into a really brutal lose-lose trade-off.
Okay, what are the options?
Your first option is analytical differentiation. That means you, the human being, sit down with a piece of paper or maybe some symbolic math software, and you manually derive the exact massive algebraic formula for the derivative of your airflow model.
Right.
Then you have to hard code that massive formula into C++ or Python or whatever.
Which, I mean, that sounds fine for a simple parabola. But for a 3D fluid dynamics model over a wing, that equation would be pages and pages long.
It results in a complete combinatorial explosion of terms. The code becomes incredibly bloated, it takes forever to compute, and it is highly, highly prone to human typo errors during implementation.
Because if you miss one negative sign on page 3,
The whole wing simulation crashes. Exactly. So because that's so painful, engineers often choose the second option, numerical differentiation.
okay, and what is that?
Specifically, they use finite difference approximations.
This is basically the guess and check method, right?
Pretty much. You tell the computer to just take a tiny step forward, subtract the previous value, and divide by the step size. Rise over run.
Yeah, basic slope.
Yes. You use a small step size, which is usually called h. But here is the fatal trap with finite differences.
Let's hear it.
If you make h too large, your straight line approximation of the curve is wildly inaccurate.
Because the real curve bends away from your straight line.
Exactly. That is called truncation error. You're losing the real shape. So a programmer thinks, okay, I'll just make h incredibly small to stay closer to the curve.
Right, let's make 1/1000th of a millimeter.
If you do that, you trigger the second trap, which is subtractive cancellation.
And that's a hardware issue, isn't it?
It is. Computers store numbers in floating point format, meaning they only have a finite number of bits to represent a decimal.
Right.
So if you take two numbers that are almost perfectly identical, say 5.000001 and 5.000000, and you subtract them, the computer has to shift the decimal and chop off the trailing digits just to fit it in memory.
Oh, wow. So you instantly lose all your significant digits.
Yes, your data literally turns into random static noise. So engineers have to spend weeks agonizing over step size tuning. They're trying to find the Goldilocks value of h that minimizes the truncation error without triggering that subtractive cancellation.
It sounds like an absolute nightmare, but the nilpotent epsilon completely sidesteps that entire valley of death, doesn't it?
Entirely. When you evaluate your function using dual numbers, the system provides exact derivative propagation down to the absolute limit of machine precision.
So there's no step size h.
No step size. There's no tuning whatsoever. You aren't approximating a curve by drawing tiny straight lines. The algebraic structure of the ring guarantees that those higher-order error terms just vanish instantly.
Because epsilon squared is 0.
Exactly. You retain a mathematically pure, compact representation of the local geometry.
Okay, that perfectly transitions us to the second massive concept in our foundational statement. The quote says, Nilpotent, quote, implement Taylor expansion algebraically, retaining a finite jet. Now, I think the scholars understand the nilpotent tool now. We get the self-destructing epsilon. But what exactly is an algebraic Taylor expansion, and what is a finite jet?
Let's ground this in classical calculus first. If you have a really complex winding curve, a Taylor series expansion is a classical method of trying to recreate the entire global shape of that curve, based solely on the information at a single point.
Right.
You start at your point and you add the first derivative, which gives you the local slope. Then you add the second derivative, which tells you how fast the slope is changing the curvature.
And the third derivative, the fourth, and so on.
Right. But to get a mathematically perfect recreation of the entire curve across all of space, you need an infinite sum of derivatives.
Which, as we established, is physically impossible to compute. Computers are finite-state machines. They cannot run a loop forever.
They cannot. So classical numerical methods just calculate the first few derivatives and then literally just chop off the rest of the infinite series.
They just stop.
They just stop. But this introduces a remainder, an unknown cloud of error hanging off the end of your calculation. You are constantly trying to bound or estimate how much error you just introduced by stopping the math early.
Enter the algebraic geometry perspective in the finite jet.
Yes. When we evaluate a smooth mathematical map on a Weyl algebra point, and remember, that is our standard real number wearing a little halo of nilpotent epsilon, it yields a coordinate-free algebraic Taylor expansion.
Okay.
But the behavior is radically different. Because our Weyl algebra contains a nilpotent ideal, we know that at some specific power, let's call it k plus 1, the epsilon term becomes exactly 0.
So unlike the classical Taylor series that wants to stretch to infinity but gets violently chopped off by the programmer, this algebraic version has a built-in natural termination point.
It stops cleanly. It truncates precisely at order k. There are absolutely no higher order remainder terms. There is no mysterious error cloud trailing behind your calculation. We call this complete, flawless package of localized information a k-jet. It is the point itself, plus its exact derivatives up to order k, bundled perfectly together.
And we aren't just limited to the first derivative, right? We can scale this up.
Considerably. So dual numbers with one epsilon give you the first derivative, the gradient. But if you need the second derivative, what we call the exact Hessian matrix, which describes the multidimensional curvature,
Right.
you construct hyperdual numbers. You introduce two distinct nilpotent variables. Let's call them epsilon 1 and epsilon 2.
Okay.
You set the rule that epsilon 1 squared is 0, epsilon 2 squared is 0, and crucially, their combined product epsilon 1 times epsilon 2 squared is 0.
Oh, I see.
This builds a second-order tangent bundle. And if you need to calculate hundreds of multivariate high-order derivatives simultaneously for like a massive neural network, you scale up to a full jet algebra.
I want to offer an analogy here for the listeners just to visualize how this changes our approach to problem solving.
Please do.
Searching for a global, exact symbolic solution to a chaotic real-world system using infinite series. It's like trying to take the globe of the Earth and peel it flat onto a single perfect piece of paper.
Like a Mercator projection.
Exactly. It is mathematically impossible to do without introducing massive distortions. Greenland looks huge, Antarctica stretches completely across the bottom. That distortion is the exact same thing as the error in a truncated infinite Taylor series.
That's a great way to put it.
Right, but a finite jet. A finite jet is like having a perfectly flawless GPS map of exactly a 10-foot radius right around your current position. For almost every practical industrial application, whether you are an autonomous drone navigating a forest or a chemical mixing tank adjusting its pressure, you do not need a perfect map of the whole Earth. You only need to know with absolute mathematical certainty how the physical space is behaving right where you are.
That is a phenomenal way to visualize it. You are trading an impossible global problem for a perfectly solved local problem. And the literature actually takes this even further. The sources describe how these local algebraic jets are extended across global spaces using mathematical tools called Weyl functors and Weyl bundles.
Okay, you are going to have to translate that for us. What does a Weyl functor actually do?
So a Wildfunkler is essentially a mapping tool. It takes a standard, smooth manifold, imagine the curved surface of an airplane wing, and it maps it to what we call a prolonged manifold.
Okay.
This new space is basically the original surface, but it's entirely constructed out of those infinitesimally thickened points we discussed
Like
earlier.
the epsilons.
Right. And the critical advantage here is the preservation of structure. When we translate the geometry into this nilpotent algebra, the geometric properties of the original space are flawlessly preserved, even under infinitesimal deformations.
Okay, give me a tangible physical example of that. What kind of properties are we preserving?
Let's say you are simulating a closed physical system on a Poisson manifold. That is a mathematical framework heavily used to model classical mechanics, like planetary orbits or fluid vortices.
Okay, orbital mechanics.
Right. It relies on a specific symplectic geometry. When you run a classical numerical simulation, all those rounding errors and the finite difference truncation we talked about, they slowly erode that geometry.
The errors pile up.
Yeah, the simulation mathematically leaks energy. Your simulated planet slowly, inevitably spirals into the sun because the math isn't perfectly conserving momentum.
But the Weil bundle fixes that leak.
It mathematically seals the system. The Weil bundle inherits a canonical Poisson structure directly from the base space.
Okay.
This guarantees that physical invariance, the foundational laws of conservation of energy and momentum, are conserved to machine precision throughout the entire simulation.
So the math forces the physics to be real.
Exactly. The geometry is locked in place by the algebra. The simulated planet stays perfectly in orbit for millions of virtual years because the nilpotent code literally won't allow the physics to break.
That level of stability is just incredible. But let me throw a wrench into this.
Bring it on.
Everything we've discussed so far assumes we're dealing with smooth, continuous physical reality. Airplane wings, planetary orbits.
Sure.
What happens if a scholar is working in discrete mathematics, say digital signal processing or quantum cryptography? Those fields often use finite mathematical fields where the rules of arithmetic wrap around on themselves, like clock math.
Right.
The sources specifically bring up Galois fields and positive characteristic P. Doesn't classical calculus just completely disintegrate to those environments?
You've highlighted one of the most fascinating blind spots in classical mathematics. Yes, in a finite field of positive characteristic P, let's say a field where the math wraps around every 3 integers, so P equals 3 standard derivatives, absolutely fail.
How do they fail?
Well, if you take a classical formal derivative of a polynomial, say x to the third power, the derivative is 3x squared.
Right, simple power rule.
But in a modulo 3 system, the number 3 is mathematically equivalent to 0, so the derivative just becomes identically 0.
Ugh. The classical derivative just goes blind. Looks at the function, tries to measure the change, and just outputs 0, stripping away all the useful information.
Exactly.
So our whole nilpotent cheat code is useless for cryptography then.
On the contrary, this is exactly where the algebraic geometry perspective proves its universal validity.
Wait, how?
Because we aren't relying on spatial limits or geometric drawings, we can swap out the classical derivative for something called the Hasse derivative, or the Hasse-Taylor operator.
A Hasse derivative.
Yeah. It redefines the concept of a derivative purely algebraically, using binomial coefficients that evaluate correctly over these finite wrapping fields.
And does the Hasse derivative still interact with our nilpotent jets?
Perfectly. The Hasse operator satisfies a generalized product rule that is completely isomorphic, structurally identical to our algebraic Taylor expansion.
Wow.
When quantum computing researchers expand code words in Hasse-Taylor coordinates, the high-order Hasse derivative operator naturally decomposes into independent local blocks.
Which means it bypasses that zeroing out problem completely.
Exactly. It allows researchers to compute the exact closed-form dimensions of what are called derivative twisted intersections.
Okay, pause right there. Derivative twisted intersections. Break down the mechanics of what that actually means in a quantum system for me.
So in quantum error-correcting codes, you have to entangle qubits to protect the data from quantum noise, but entanglement is computationally expensive.
Right.
You are looking at the intersection of different vector spaces representing the data. A twisted intersection means the data spaces are shifted or modified by a derivative operator to optimize that entanglement.
Okay.
By using the Hasse-Taylor algebraic structure, engineers can literally tune the derivative order to perfectly calibrate the entanglement cost of the quantum code.
That's amazing.
So this nilpotent framework isn't just a trick for rendering smooth curves. It is a fundamental skeletal structure of mathematics that scales from physical fluid dynamics all the way down to the architecture of quantum computing.
That is genuinely mind-bending. I mean, we have officially decoded the foundational statement. The theory is completely locked in.
I think they've got it.
Now, we are going to pivot. The quote promises practical industrial applications. It is time to see how this theoretical skeleton key actually unlocks massive real-world industries.
Let's do it.
Let's start with the chaotic, invisible world of thermodynamics and chemical engineering.
It is the ultimate testing ground for this math. Process engineers at massive chemical refineries have to model the state properties of complex, multi-component fluid mixtures.
Like, imagine a pipe carrying a high-pressure mixture of methane, ethane, propane, and heavier hydrocarbons all at once.
Exactly. And the engineers need to calculate thermodynamic potentials, specifically the Helmholtz energy density, to predict exactly how that fluid will behave under different temperatures and pressures.
And calculating that energy density isn't a simple algebra equation, right? It requires knowing how every single variable shifts in relation to every other variable.
It requires an absolute avalanche of derivatives. If a safety engineer needs to know the exact thermodynamic speed of sound traveling through that chemical mixture,
Or the isobaric heat capacity to design a cooling system.
right, they need mixed partial derivatives. And if they want to find the critical loci, the exact temperature and pressure where the liquid phase and gas phase literally become indistinguishable from each other.
That critical point.
Yes. For that, they need second-order and third-order mixed partial derivatives.
And they need those derivatives evaluated with respect to temperature, volume, and the individual molar concentrations of every single chemical in the pipe.
Yeah.
I mean, if you have 10 chemicals, the sheer combinatorial math of finding every mixed cross-partial derivative must be absolutely staggering.
It is a complete computational nightmare. Traditionally, engineers faced the two bad options we discussed earlier. They either used manual analytical differentiation, writing thousands of lines of bespoke brittle code to track every single derivative equation.
Practically ensuring a human typo somewhere.
Exactly. Or they used finite differences, taking those tiny step sizes h.
But in thermodynamics, that guess-and-check finite difference method is a disaster, right? Because the landscape of the math is so steep and nonlinear.
It is catastrophic. When you are calculating third-order derivatives using finite differences, you have to subtract these tiny approximated values over and over and over again.
And we know what happens there.
The subtractive cancellation completely destroys your precision. The error compounds exponentially with every order of derivative you take. You end up making multi-million-dollar plant design decisions based on mathematical static.
So we inject the Nilpotent cheat code, hyperdual numbers.
Yes. By implementing hyperdual numbers, the process engineer writes the code for the base thermodynamic model just once.
Just once.
They feed the hyperdual variables into it, and in a single computational pass, the algorithm calculates the exact mixed second derivatives simultaneously.
No step-size tuning.
No step-size tuning, no infinite error tails. It is exact down to machine precision.
And the literature highlights specific open-source libraries that are doing this in the wild right now, doesn't it?
It does. Libraries like the templated equation of state package-clapeyron.jl.
Right. These libraries are utilizing this exact algebraic geometry perspective. They demonstrate that insanely complex, industry-standard thermodynamic models like PCSAP can be evaluated incredibly fast with absolutely zero loss of numerical precision.
Let's dig into the actual mechanics of a critical calculation they perform. The sources discuss finding critical points using the Heidman and Khalil algorithm.
Okay, how does that work?
In this algorithm, the software has to assemble and evaluate a massive matrix called the M matrix. The M matrix is entirely constructed out of the second partial derivatives of the Helmholtz energy with respect to the mole numbers of the chemicals.
And hyperdual numbers populate that matrix flawlessly. But the real bottleneck is the next step, right?
Yes, the second criticality condition.
Explain that.
To prove a fluid is definitively at a critical point, you need a third-order derivative. Normally, calculating this third-order derivative introduces massive numerical noise directly into the residual function of the system's solver.
It causes the algorithm to just bounce around without ever converging on the true answer.
Exactly. But by extending our algebra to third-order dual numbers, where the nilpotent element truncates exactly at epsilon to the fourth equals 0, an engineer evaluates the Helmholtz energy once.
Just one time.
Yes, the base output is the energy. The epsilon 1 and epsilon 2 slots hold the matrix data, and the epsilon 3 component automatically catches the exact noise-free second criticality condition.
One flawless evaluation pass.
One pass.
Okay, but what about molecules that don't just bounce off each other smoothly. The sources talk about cross-association models. What does that mean physically?
In advanced models like SEFT, you have to account for hydrogen bonding. These are highly directional, short-range interactions where molecules physically link up and pull on each other.
Like water molecule.
Exactly. The mathematical contribution of these bonds to the Helmholtz energy relies on calculating the fraction of non-bonded sites in the fluid.
But calculating that fraction is a paradox, isn't it? It's an implicit equation.
It is entirely implicit. The answer depends on the answer. The computer basically has to guess a fraction, run the physics, see how wrong it is, adjust the fraction, and repeat.
Right.
It's called a Newton iteration scheme. And to find the overall derivatives of the Helmholtz energy for the plant design, you need the derivatives of those monomer fractions at the exact same time.
Which means tracking derivatives inside a recursive loop.
Which normally breaks numerical solvers in half, but with generalized dual numbers, you simply run the Newton iteration using the dual numbers themselves.
Ooh.
Yeah. As the base value converges on the true fraction, the nilpotent epsilon terms automatically carry and refine the exact derivatives alongside it. It requires almost zero additional code architecture.
Okay, I have to push back here on the hardware reality, though.
Okay, let's hear it.
We are talking about evaluating third-order mixed partial derivatives, tracking implicit recursive loops across 10 different chemical concentrations. Even if the algebra is elegant, aren't we just trading a mathematical headache for a massive computing bottleneck?
It's a fair question.
I mean, if the computer has to evaluate every single combination of variables, doesn't the computational workload explode into, like, days of processing time?
That is the absolute genius of the compiler-level mixed derivative optimization detailed in the research.
Okay, break that down.
In standard computational machine learning, if you want high-order mixed derivatives, the software builds nested schedules of forward and reverse mode automatic differentiation.
Basically forcing the computer to build a massive, sprawling graphical map of the equations.
Right, and then it traces paths backward and forward through that map for every single variable.
A computational graph built on top of another graph, it scales combinatorially. It just eats up all the RAM.
Exactly. But when you utilize tensorized Weil algebras, this combinatorial nightmare completely vanishes. Because the Weil algebra natively, structurally encodes the complete algebraic jet of a given order, evaluating a function on a tensorized Weil algebra computes all the mixed derivatives in a single forward computational sweep.
Wait, a single pass. It doesn't have to trace back and forth for every chemical.
Just one forward pass. The computational complexity shifts from scaling combinatorially with the derivative order to scaling linearly with the dimension of the Weil algebra.
That's huge.
It fundamentally changes the math of the processor. Furthermore, because these algebraic structures are so rigid and predictable, you can compile these high-order sensitivity equations directly into highly optimized low-level GPU kernels using frameworks like JAX.
Wow.
Yeah, you get perfect precision at linear scaling running natively on massive parallel processors.
So we contain the unpredictable high-pressure chaos of millions of molecules using nilpotents. But what happens when the chaos isn't microscopic molecules, but massive physical machines moving through the real world?
Right, macrophysics.
Let's move to our second industrial application, non-holonomic robotic trajectory optimization.
Okay, first, we really have to unpack what non-holonomic actually means.
Yes, please.
A holonomic robot, say, a drone flying in open air or a hovercraft, can generally move freely in any direction within its configuration space. If it wants to move left, it thrusts left.
Simple.
But a non-holonomic system has severe velocity constraints built into its physics. These constraints cannot be mathematically integrated into simple position coordinates.
Okay, to put that in everyday terms for you guys listening, think of driving a car. You can drive forward, you could drive in reverse, and you can change the angle of the front wheels to steer.
Right.
But you cannot instantly slide the car perfectly sideways to the left. The physics of the tires rolling on pavement constrain you. You are locked out of that dimension of direct movement.
Exactly. The sources highlight two notoriously difficult non-holonomic systems in robotics. The first is the ball-on-a-plate mechanism, where a robotic platform has to balance and roll a sphere without ever allowing it to slip or slide.
The constraints on that are maddening.
They really are. And the second is the car with trailers problem. Imagine a robot tug pulling 3 jointed trailers behind it through a tight factory.
Oh, man.
Every single axle and hitch adds a compounding non-holonomic constraint. The math gets terrifying very quickly.
Why can't engineers just use standard robotic navigation software for this?
Because classical linear control design relies on taking the wildly complex nonlinear dynamics of a robot's physical movement and creating a first-order tangent linearization.
Basically, the software creates an approximate straight-line mathematical model of the robot.
Right, but here's the fatal flaw. For a non-holonomic system, this first-order tangent linearization is completely uncontrollable.
Because a straight-line approximation of a car doesn't comprehend the ability to steer, reverse, and wiggle sideways.
Exactly. The linear software model looks at the car and says, you want to move 2 feet to the left. Error. Movement impossible. Command rejected. Classical linear control simply gives up.
But in physical reality, these systems are controllable. I mean, you can parallel park your car into a tight space.
Right. The controllability doesn't come from straight lines. It comes from the Lie brackets of the control vector fields.
Lie brackets. Let's dig into the mechanics of this. In the math, it's often written as the bracket of two vectors, f1, f2. What is happening physically when a lie bracket is executed?
So a Lie bracket is basically the mathematical formalization of a wiggle.
A wiggle.
Yeah. It describes the net macroscopic movement that is generated when you combine forward and backward microscopic movements in specific alternating patterns.
Okay, imagine you are parallel parking. You cut the steering wheel hard right and back up a few feet. That vector is f1.
Right.
Then you cut the wheel hard left and pull forward a few feet. That vector is f2. You alternate right back, left forward, right back, left forward.
And none of those 4 individual movements are slide the car directly sideways.
No.
But the combination of those movements, the Lie bracket of the alternating vector fields, generates net motion in a completely new direction that was previously blocked by the non-holonomic constraint.
The lie bracket mathematically spans the tangent space, allowing you to slide sideways into the parking spot.
Exactly. And this brings us right back to our algebraic geometry. We know we can't use the useless linear approximation, so what do?
We construct a nilpotent approximation?
Yes. We construct a nilpotent approximation of the control vector fields. We inject our self-destructing epsilon into the robot's navigation matrices.
Wow.
The complex nonlinear dynamics of the physical robot are replaced by a nilpotent Lie algebra of order k. Because the nilpotent element guarantees the algebra truncates cleanly, it yields a triangular polynomial system that the computer can actually integrate in closed form.
We generate a perfect finite jet of the local movement possibilities, explicitly including all those lie bracket wiggles.
Yes, exactly.
And the sources describe a brilliant navigation strategy that uses this math, called the Ariadne thread strategy. How does a robot use an Ariadne thread to navigate a factory?
It relies on Suber-Riemannian geometry. Imagine the factory is filled with obstacles and you have to get your car and 3 trailers from point A to point B.
Okay.
Step 1 of the algorithm. Ignore the wheels completely. Ignore the physics. Just calculate a smooth, collision-free line through the factory. That impossible, purely geometric path is the Ariadne thread.
But the robot can't actually drive that thread, because the thread might require the trailers to slide sideways like crabs to get around a tight corner. It is a non-admissible path.
Precisely. So step 2, the algorithm uses the nilpotent Lie approximation to calculate the exact admissible path, the highly complex sequence of forward, reverse, and steering angle adjustments that stays epsilon close to the thread.
It calculates the optimal parallel parking wiggles required to perfectly track the physically impossible path.
Exactly. And the literature contrasts this exact algebraic method with classical navigation, which used ordinary, Lissajous-like out-of-phase sinusoids.
Basically just applying rhythmic sine waves to the steering column to make the robot wiggle blindly.
Which is wildly inefficient and slow. The text demonstrates that by utilizing the rigorous nilpotent structure, engineers can integrate the system using hyperelliptic curves.
Hyperelliptic curves.
Right. Through an iterative steering framework, these algebraically derived control laws are vastly faster and more precise than sine wave guessing.
Okay, I need to interrupt here on behalf of real-world physics again.
Go for it.
In a flawless computer simulation, a hyperelliptic curve works perfectly.
Ugh.
But the real world is chaotic.
Yeah.
The factory floor has bumps. A wheel bearing is slightly rusted. A tire is slightly deflated, changing its radius.
Ugh.
Doesn't the robot constantly recalculating its position in this highly rigid, nilpotent airspace just cause a mathematical crash when reality doesn't match the model?
You've hit on the most crucial requirement for industrial robotics, which is robustness. And this is where the algebraic approach shines brightest.
How so?
Because these hyperelliptic control laws are applied in a continuous feedback loop directly over the exact nilpotent Lie approximation, The mathematical framework guarantees asymptotic stability with exponential convergence.
Translate asymptotic stability with exponential convergence into how the robot reacts to that deflated tire.
Okay, it acts basically like an invisible tractor beam. If the tire is deflated, the robot will start to drift off the mathematically optimal path.
Right, because it's pulling to one side.
Exactly. But the nilpotent feedback loop instantly measures that deviation and algebraically recalculates the local jet. Because the convergence is exponential, the further the robot drifts, the harder the control law forces it back to the baseline.
It naturally autocorrects.
Yes. It provides robust rejection of physical perturbations and model uncertainties, smoothly absorbing the error without breaking the algorithm.
Okay, so we've gone from the chaotic forces of fluid dynamics to the physical friction of robotic tires. Now, we move to a domain where the entire objective is purely geometric. We're rendering digital shapes on a screen.
Ah, yes.
Let's tackle our final industrial application: CAD, computer graphics, and character skinning.
Let's look at computer-aided design, or CAD. This is the foundational software architecture used to design physical reality. Everything from the curvature of a stealth bomber wing to the internal housing of a smartphone is designed in CAD.
Right.
And a core constant computational task in CAD is computing the intersections between complex parametric curves and 3D surfaces.
So the software has two complex 3D objects, and it has to calculate the exact mathematical boundary where one slices into the other.
Standard numerical methods handle simple intersections fine. Two spheres intersecting. Easy. But numerical solvers fail catastrophically near geometric singularities.
What does a geometric singularity actually look like in CAD?
Imagine a curve that bends around and perfectly kisses itself, creating a cusp or a self-intersection. Or imagine two undulating surfaces that don't slice through each other cleanly, but share a high-order contact point. They are perfectly tangent, grazing each other along a microscopic twisting edge.
Oh, I see.
Numerical solvers panic at these singularities. They look at the math, see multiple overlapping solutions or no clear gradient to follow, and the software just crashes, or it creates jagged, corrupted geometry.
So how does the algebraic geometry perspective untangle a singularity?
We rely on a massive breakthrough introduced in 1968 by the legendary mathematician John F. Nash.
The Nash equilibrium guy.
The very same. He introduced the concept of jet schemes and arc spaces to study the intrinsic properties of these singularity resolutions.
Jet schemes. That is directly related to the finite jets we've been tracking this whole time. Right?
Exactly the same lineage. For a geometric scheme X defined over a field, the nth jet scheme retains the finite algebraic jet of that geometry. By upgrading CAD algorithms to operate on these jet schemes, the software can determine the exact mathematical order of contact and resolve the singularities algebraically, completely ignoring the numerical guesswork.
Let's get into the hood of the code here. How does the software actually use a nilpotent element to resolve two objects perfectly kissing each other?
So the nilpotent elements in the coordinate ring of the jet scheme mathematically represent the local tangent cone at the exact point of singularity.
Visualize that for me. A local tangent cone.
Imagine the exact microscopic point where the two surfaces graze each other. Now imagine a mathematical cone originating from that exact point, flaring outward.
Okay, I see.
That cone perfectly encapsulates all the possible directional vectors and tangent paths radiating from that singularity. The nilpotent algebra algebraically defines that cone.
Wow.
By analyzing the nilpotent structure, the algorithm perfectly isolates the intersection curves. It acts like a mathematical magnifying glass, bringing the local geometry into absolute flawless focus, entirely bypassing the impossible task of solving a global nonlinear equation.
It is so elegant. Now let's transition from static industrial design to kinetic entertainment, computer animation.
The fun stuff.
This brings us back to the scenario we opened the deep dive with: the collapsing candy wrapper shoulder of the video game character. Why is this such a persistent problem in the industry?
It all comes down to a process called character skinning. When an animator builds a 3D character, they build two things: an invisible internal skeletal rig made of joints and bones, and a 3D polygonal mesh, the skin that is wrapped around it.
Right.
When the animator rotates the invisible shoulder joint, the game engine has to instantly calculate how the thousands of individual polygons making up the bicep and shoulder should deform and stretch to follow the bone.
And for decades, the industry standard for calculating that stretch has been a matrix map approach called linear blend skinning, or LBS.
Exactly. LBS relies on standard 4x4 transformation matrices to calculate movement, and it possesses a fatal mathematical flaw. Standard 4x4 matrices do not interpolate complex rotations smoothly. When you try to linearly blend the math of the arm bone twisting with the math of the collarbone twisting, the matrix math essentially cuts corners.
It calculates a shortcut through the geometry.
Yes, which physically manifests as the 3D mesh collapsing in on itself. Volume is destroyed. The shoulder pinches into that flat, twisted candy wrapper.
So we inject the nilpotent. How does it save the geometry?
Through an incredibly elegant evolution of the math called dual quaternion linear blend skinning, or DQLBS.
Dual quaternions.
Right. A dual quaternion is built directly on top of our old friend, the nilpotent dual unit, where epsilon squared equals 0.
That is wild. The exact same epsilon that solved the chemical plant's thermodynamics is now rendering the video game sword swing.
Exactly. A dual quaternion leverages this nilpotent structure to encode both rigid body rotation and spatial translation simultaneously into a single unified algebraic structure.
Okay, so they're locked together.
Because the rotation and the translation are permanently bonded together by the underlying algebra of epsilon, when the game engine interpolates between two dual quaternions, say, twisting the arm from 0 degrees to 90 degrees, the rotation is mathematically forced to travel perfectly along the shortest possible path on a multidimensional sphere.
It's mathematically impossible for the geometry to collapse.
The volume is perfectly preserved. The candy wrapper effect is completely eradicated.
I have to bring up the hardware reality again, though. In video games, performance is literally everything.
Oh, for sure. Frames per second.
Right. The GPU has to render these characters at 60 or 120 frames per second, processing millions of polygons in milliseconds. If we were replacing standard matrices with highly complex multidimensional dual quaternions, doesn't that massive mathematical overhead melt the graphics card?
That is the ultimate twist of this entire deep dive. Moving to the more advanced algebraic geometry actually makes the hardware run vastly faster.
Wait, how? You just added layers of complex algebra.
But the resulting algebraic representation is incredibly compact. To define a standard 4x4 transformation matrix for the flawed linear blend skinning, the computer requires 16 separate parameters, a grid of 16 floating point numbers.
Okay.
But a dual quaternion, despite mapping complex 3D rotations perfectly, requires only 8 parameters to encode the exact same movement.
You just cut the data payload exactly in half.
A 50% reduction in transform data size. When a GPU is pushing millions of vertices through a rendering pipeline 60 times a second, processor speed isn't the bottleneck. Memory bandwidth is.
Getting the data from the RAM to the cores.
Exactly. By having the data footprint with dual quaternions, you dramatically optimize execution on parallel GPU hardware. You achieve mathematically flawless, candy wrapper-free animation, and it renders faster, cheaper, and cooler than the flawed legacy method.
Wow. Let's take a breath and just zoom all the way out.
It's a lot to take in.
It is. We have traced an astonishing through line today. We started with the most abstract reaches of theoretical mathematics, inventing a nilpotent number that squares to 0. And we watched that single structural truth propagate out to stabilize the chaotic fluid dynamics of a chemical plant, mathematically guarantee the precise parallel parking of a massive robotic trailer, and flawlessly render the kinetic movement of a digital character while actually saving processing power.
It's everywhere.
To the Sigma scholar still tracking with us, this is the toolkit.
It is a profound demonstration of why theoretical rigor matters in the physical world. The overarching lesson here is that relying on continuous approximations, hacking physical reality into tiny straight lines, and using finite differences inevitably leads to truncation errors, subtractive cancellation, and combinatorial explosion.
It's a dead end.
It is. By embracing the algebraic geometry perspective of nilpotence, we retain finite jets. We capture the exact local Taylor expansion perfectly bounded, which completely bypasses the chaos of numerical approximations.
We eliminate the cascading errors. We reduce impossible combinatorial computation down to predictable linear scaling. And we achieve robust stability in nonlinear constrained physical spaces where classical control methods just throw their hands up and crash.
That is the fundamental takeaway. When you transition from classical numerical hacking to structure-preserving, algebraic geometric frameworks, you guarantee stability, precision, and efficiency simultaneously.
And this is exactly why this knowledge is vital for you, the true scholar. The elite advantage in any field engineering, computer science, physics isn't found by just grinding harder.
No, it's not.
It isn't achieved by running millions more iterations of a flawed finite difference algorithm, just hoping the noise eventually cancels itself out. Your advantage is in discovering the elegant, mathematically true framework underneath the problem.
Finding the root.
Exactly. It is about deploying the exact right tool, like a self-destructing dual number, that instantly makes the impossible beautifully solvable.
It is the definition of working smarter. You let the profound structural truths of the mathematics do all the heavy lifting for you.
Precisely. Now, before we sign off, I want to leave you with one final, deeply provocative thought to mull over.
I love these.
It builds on everything we've explored today, but it stretches past engineering and right to the edge of theoretical physics and cosmology. We discussed earlier how using while bundles ensures that, quote, physical invariants are conserved to machine precision.
Right. The Nilpotent algebra mathematically locks in the symplectic geometry of a Poisson manifold, guaranteeing that energy and momentum never leak out of the simulation.
It forces the simulation to perfectly obey the laws of physics without that phantom energy loss you see in numerical approximations.
Exactly.
So consider this. If abstract, localized algebraic tools like nilpotent infinitesimals and finite jets map so perfectly, so flawlessly onto the physical laws of our universe, modeling the conservation of energy better than the infinite continuous real number line ever could, does that imply something fundamental about the architecture of reality itself? Does it imply that the deepest quantum fabric of space-time doesn't actually operate on a smooth, infinitely divisible, continuous continuum?
Oh, wow. That is a staggering implication. You're suggesting the universe itself might be fundamentally algebraic, built on discrete, self-truncating local jets, rather than the smooth infinity of classical calculus.
Is the source code of reality written in while algebras? It is something to sit with the next time you look up the chaotic orbits of the stars, or, the next time you marvel at a flawlessly rendered video game.
It really makes you think.
Thank you for taking the deep dive with us today. Keep questioning the code, keep digging for the structure, and we will see you next time.